Okay, so today I'm going to talk about liveness properties in transactional memory systems by Victor Bushkov, Rachid Guerraoui, and Michał Kapałka. In this talk, I consider a general shared memory system in which threads of some concurrent application communicate with each other by performing operations on shared objects. One way to synchronize accesses to these shared objects is through the use of locks, when a thread needs to acquire an exclusive lock before accessing a shared object. However, locks have several problems. First is the problem of deadlocks and live locks, when a thread never completes its operation because it waits for some other thread holding a lock. Second is the problem of priority inversion, when a higher priority thread is preempted by a lower priority thread to make progress. The third problem with locks is that locks in general do not allow composability of operations. Lastly, there is a trade-off between fine-grained locking and coarse-grained locking. Coarse-grained locking is easy to implement but reduces parallelism. On the other hand, fine-grained locking is hard to implement and is prone to errors. Transactional memory is a synchronization mechanism which is an alternative to locks and which avoids some problems associated with locks. It provides a programmer with an abstraction called transaction. Threads can access shared objects only within transactions. When a thread needs to perform an operation on a shared object, it starts the transaction. Then it performs operations on the objects, and then it requests the transaction to commit. If the transaction commits, then all the changes made within operations within transactions are made visible and appear as if they are executed at some instant moment of time. If the transaction aborts, then all the changes made by operations within the transaction are discarded. The correctness of a concurrent application using a transactional memory depends on the correctness of the transactional memory implementation. Therefore, it is important to ensure that the implementation is correct. The correctness of an implementation is specified through two kinds of properties: safety properties and liveness properties. However, there is a fundamental trade-off between these two kinds of properties. For example, strong liveness properties might make it impossible to implement strong safety properties, and vice versa. Strong safety properties might make it impossible to implement strong liveness properties. Roughly speaking, a safety property states that some bad events never happen. Examples of such properties in transactional memory context are serializability, strict serializability, and opacity. On the other hand, a liveness property requires that some good events eventually happen. The examples of common liveness properties for shared objects are abstraction freedom, lock freedom, and wait freedom. Roughly speaking, these properties state that certain threads should make progress, where a thread makes progress if its operation eventually terminates. However, in transactional memory context, requiring such liveness properties alone will not be enough to ensure any meaningful progress. Threads of which all transactions are aborted might be satisfying wait freedom, but will not be making real progress. Thus, the first question we address in our work is how to define liveness property in transactional memory context. So, to do this, we first define what does it mean for a thread to make progress. We say that a thread makes progress in an infinite history if infinitely many transactions of the thread commit in that history. However, we cannot always require a thread to make progress. There are two cases when we cannot do that. The first case is when the thread crashes, that is when the thread stops taking steps. The second case is when a thread is parasitic, that is when the thread invokes infinitely many operations within a transaction without invoking a commit request. We can require progress only for the correct threads, that is threads which are neither crashed nor parasitic. We define a transactional memory liveness property as a weakening of the strongest liveness guarantee in the given context, which we call local progress, and which is analogous to wait freedom. Local progress requires that every correct thread makes progress. Using this definition, we can define different weakenings of local progress. For example, global progress, which is analogous to lock freedom, requires that at least one correct thread makes progress. This property is weaker than local progress. Solo progress, which is analogous to abstraction freedom, requires that a thread makes progress if it is the only thread that takes steps. There are implementations that ensure opacity and global progress. However, if we require a stronger liveness property, then it might be impossible to guarantee some safety properties, like opacity or strict serializability. So the question is, what liveness properties are impossible to implement together with common safety properties? To answer this question, we define a class of liveness properties called B-progressing liveness properties, which includes liveness properties that require progress for at least two correct threads. This class includes progress. This class includes local progress, but does not include global progress, since every B-progressing liveness property is stronger than global progress. And we show that in a fault-prone system, that is a system in which processes can crash or be parasitic, it is impossible to guarantee both strict serializability and a B-progressing liveness property. For example, ensuring local progress in an asynchronous system results in violation of strict serializability. The intuition behind the impossibility result is the following. Consider two threads. The first thread starts the transaction T1 and reads from a shared register. Then the second thread starts transaction T2 and also reads from the shared register. After that, the second thread writes to the register and requests to commit transaction T2, while the first thread does not do anything. A transactional memory implementation doesn't know if the first thread is crashed or suspended. Thus, to ensure progress, the implementation eventually commits transaction T2. After transaction T2 is committed, the first thread resumes taking steps and writes to the register and requests transaction T1 to commit. However, since the transactional memory implementation has to ensure strict serializability, transaction T1 is aborted. Such situation can be repeated infinitely often, thus resulting in a history in which the first thread, which is correct, does not make progress. So what does the impossibility result mean? It means that a programmer implementing transactional memory needs to find alternatives to circumvent the result. One way to circumvent the impossibility result is to assume that transactions are static and predefined from the start. In that case, transactions can be viewed as simple operations, and one can apply classical universal construction to ensure local progress. The second way is to consider a different system model. For example, it was shown that it is possible to ensure local progress in an asynchronous multi-core system model, which assumes that a transaction can be executed by different threads and that some threads crashes are detectable by a runtime system. The third way is to weaken safety or liveness property requirements, for example to require only global progress or considering some weaker safety properties.